Hi everyone, welcome back to my channel. Today I came with a new topic, that is photochemistry. Photochemistry is one of the important topics in UG, that is UG level as well as in PG level. Both undergraduate and postgraduate level photochemistry is there. So here we are discussing some of the important topics under this photochemistry. Now, what is photochemistry? As we know, photochemistry is the branch of chemistry which deals with the study of chemical changes brought about by radiation. When a substance absorbs radiation, some chemical changes may take place. Such chemical changes are called, chemical reactions are called photochemical reactions, and the study of such chemical reactions, it is known as photochemistry. So photochemistry, it is a study of chemical reaction brought about by radiation. So absorption of radiation is a must, a necessary condition of photochemical reaction. So we know what is thermal reaction. The reaction brought about by absorption of heat. So difference between thermal reaction and photochemical reaction. In thermal reaction, heat is absorbed. The presence of light is not at all required. Even in dark, thermal reaction will take place. Even in dark, thermal reaction will take place. But here, the presence of radiation is necessary. The second difference, in some of the photochemical changes, in some of the photochemical reactions, the free energy of the system will increase. Not in all cases, in some of the photochemical reactions, free energy will increase. Increase in free energy. Increase in G. Remember, not in all photochemical reactions, in some of the photochemical reactions, free energy increases. But in thermal reactions, normally free energy decreases. The third one, the sensitization. We will discuss it later. It is highly selective. That is, a particular sensitizer cannot brought about all reactions. A particular sensitizer can sensitize a particular reaction. But in the case of thermal reaction, sensitization is a general reaction. It is a normal reaction. There is no such selectivity in thermal reaction. So these are the few differences between photochemical reaction and thermal reactions. A lot of differences are there, but here a few differences. Then, suppose when radiation passes through an absorbing substance. Radiation passes through an absorbing substance. What are the different changes taking place? When the radiation passes through an absorbing substance, it may undergo some chemical changes, or that radiation may cause the rotation of the molecule, or the intensity of the radiation decrease. So many things will happen when a radiation passes through an absorbing substance. One of the important rule governing a photochemical reaction or the decreasing intensity of radiation, that is Beer-Lambert law. Beer-Lambert law. First one is Lambert law. As the thickness increases, thickness of the medium through which the radiation is passing increases, the intensity going on decreasing, or decrease in intensity also increases. Right? Here the intensity decreases lesser compared to this medium. Here the thickness is very high, so here the decrease in intensity is very high compared to this one. So according to this law, decrease in intensity dI with the thickness, where x is the length or thickness we can say. Decrease in intensity, we are putting a negative sign here because the intensity is decreasing. So the decrease in intensity with thickness is proportional to intensity of the incident radiation. Intensity of the incident radiation. We can put it as I0, where I0 is the intensity of the incident radiation. And the second law, Beer's law, according to this law, as we know, the intensity decreased with the thickness. Obviously, the intensity decreased with thickness, and that intensity decreased with the thickness is proportional to intensity of the incident radiation, that is Lambert law. The same thing, that is decrease in intensity with thickness is proportional to concentration of the solution or the concentration of the medium. As the concentration increases, the decrease in intensity also increases. A greater decrease in intensity observed when the concentration of the medium increases. Comparing these two, this is because as the concentration increases, a greater decrease in intensity is because as the concentration increases, number of particles increases, and each and every particle will absorb radiation, so the intensity decreases. So combining these two, we get Beer-Lambert law. So according to Beer-Lambert law, the decrease in intensity with thickness is proportional to intensity and concentration. So when a monochromatic light is passing through an absorbing medium, the decrease in intensity is proportional to intensity of the incident radiation as well as concentration. This law is known as Lambert-Beer law or Beer-Lambert law, and we can put it as dI by dx is equal to K I C, where K is proportionality constant. And rearranging this, we get minus dI by I0. We can put it as I0 is equal to K C into dx. Just rearranging. Now we can change the sign also, that is dI by I0 is equal to minus Kc dx. Integrating this, I0 to Ix. You can say, or I0 to I, simply I0 to I. Here also 0 to x. Here also 0 to so we get ln I by I0 is equal to minus Kc into x. Ln I by I0 is equal to Kc by x. Taking common log, so we get 2.303 log I by I0 is equal to minus Kc into x. On rearranging, we get log I by I0 is equal to minus k by 2.303 cx. Again, just rearrangement, we get log I0 by I, which is equal to k by 2.303 into cx. And here we can put this as log I0 by I as A, where A is absorbance, and K by 2.303 is equal to epsilon, and which is molar absorptivity constant or molar extinction coefficient or molar extinction constant, molar absorptivity constant or a molar extinction constant. Then we get an equation like this, A is equal to epsilon Cx. This is our Beer-Lambert law. Then here also we can write it as log I0 by I is equal to epsilon Cx. And we know epsilon is molar absorptivity constant or molar extinction coefficient, and which can be given as equal to Cx log I0 by I. Okay. So suppose when concentration is 1 molar and thickness is also taken as unity, thickness of the medium, and suppose I is equal to 1/10 of I0, 1/10 of I0, that is the final intensity of the transmitted radiation, which is 1/10 of the intensity of incident radiation. And we get epsilon is equal to, not x, C is equal to 1 molar and I is equal to 1/10 of I0. Not x. Then log I0 by I. Then log I0 by I is equal to log I0 by I0 by 10. Okay, so we get log 10. This I0 and I0 cancel, this 10 comes up. So we get log 10, which is equal to 1. So this part become 1 and C is equal to 1. So obviously epsilon is equal to by x. So this like this, that is x comes here, okay. So there is a mistake, I think. That is log I0 by epsilon is equal to 1 by Cx into log I0 by I. Okay. Then when C is equal to 1 and log I0 by I is equal to log 10, then obviously epsilon is equal to 1 by x. I made a mistake. So we can define epsilon, that is molar extinction coefficient, molar absorptivity coefficient, as the reciprocal of the thickness of a 1 molar solution which reduces the intensity of the radiation to 1/10 of its initial intensity. So epsilon is defined as the reciprocal of the thickness of 1 molar solution, which reduces the intensity to 1/10 of its initial intensity. That is molar extinction coefficient or molar absorptivity coefficient. Again, we wrote as A is equal to epsilon into Cx. The ratio of the transmitted intensity to incident intensity, which is known as transmittance. That is T. And we know log I0 by I is equal to A. So we can put it as A is equal to minus log or log T is equal to minus log A, whatever it may be. So the relation between absorbance and the transmittance. Then so far we discussed what happens when a radiation passes through an absorbing medium. Regarding the intensity, now some chemical changes may take place. When a radiation passes through a medium, some chemical changes may take place. So the laws governing the chemical changes, we have two laws which governs the chemical changes when a radiation passes through an absorbing medium. The first one is Grothus-Drapper law. It is also known as first law of photochemistry. First law of photochemistry. According to this law, only radiations which are absorbed by the system, are efficient to brought about chemical changes. Only radiations which are absorbed will initiate chemical reaction. Only those radiations which are absorbed by the system can only initiate photochemical reaction. So when a radiation passes through a medium, if a molecule does not absorb any radiation, then no chemical reaction takes place. When this medium does not absorb any radiation, any frequency, then no reaction will happen. That's only radiation that those are absorbed can initiate photochemical reaction. The converse is not true. All radiations absorbed initiate photochemical reaction. It is not true. It is not true. But for photochemical reaction to take place, absorption will happen. Absorption should happen. Photochemical reaction to be taken place, absorption of radiation should be happened. But all those radiations absorbed may not bring about chemical reaction. There are some criteria. The absorbed radiation should possess minimum energy in order to bring about that reaction. So not all absorbed radiation will initiate chemical reaction. But for chemical reaction to take place, absorption should be happened. That system must absorb radiation. So the converse is not true. That is, all radiation absorbed by the system do not bring about the chemical reaction. All those radiations which have sufficient energy can bring about chemical reaction. Okay, so for a reaction to be taken place, that system should absorb radiation. So according to this law, only those radiations which are absorbed by the system can initiate photochemical change. The second one is Stark-Einstein law. Stark-Einstein law of photochemical equivalence. Photochemical equivalence. Stark-Einstein law of photochemical equivalence, and it is also known as second law of photochemistry. Second law of photochemistry. According to this law, when a radiation passes through an absorbing system, each molecule absorbs one quantum of energy. Each molecule will absorb one quantum of energy. That is, when a radiation passes through an absorbing system, each molecule will absorb one quantum of energy and undergo chemical reaction. That means all molecules which undergo chemical changes absorb one quanta each. That is, we know one quanta, energy of one quanta is equal to h nu. When a radiation passes through a sample, each molecule present in this sample absorb one quantum and undergo chemical changes. Suppose there are Avogadro number of particles present in this sample, n0. Avogadro number of particles are present in our system. Then, according to this law, each molecule absorb one quantum of energy and undergo chemical reaction. So, n0 molecules, n0 particles absorb n0 quanta. n0 quanta. So, the total energy of this n0 particle, which is equal to E is equal to n0 into h nu. n0 into h nu. You can put it as E is equal to n0 hc by lambda, because we know nu is equal to c by lambda. And the energy absorbed by one molecule of absorbing substance, it is known as 1 Einstein. 1 Einstein. 1 Einstein is equal to 1 mole of quanta. 1 mole of quanta. So here, by substituting the value of n0, that is Avogadro number, h Planck's constant, and c is the velocity of light, we get total energy of 1 mole of particles which absorb 1 mole quanta. That is 1 Einstein. It is equal to 0.0117 by lambda joule per mole. So we discussed two laws governing the absorption of light followed by chemical reaction. Then another point we are discussing here, it is quantum yield. That is the total product obtained when a definite amount of quanta absorbed by an absorbing system. Quantum yield, it is represented by phi. Phi is equal to number of molecules undergo reaction at a given time divided by number of quanta absorbed and so it is the number of molecules undergo chemical reaction at a given time divided by number of quanta absorbed at the same time. Or it is the number of molecule undergo chemical reaction per quanta absorbed. Suppose there are 100 molecules. According to second law, that is Stark-Einstein law, each molecule absorbs one quantum. So total number of quanta absorbed is 100 quanta. So quantum yield phi is equal to number of molecules undergo chemical reaction expected, not true, expected is 100 divided by number of quanta absorbed, which is 100, which is equal to 1. So quantum yield of every photochemical reaction that is expected value, it is 1. But actually it is not 1. Only one case, that is we are getting SO2 plus Cl2 gives two just a minute. Okay, SO2, Cl2. That's the only reaction which gives a quantum yield of 1. And most of the cases the quantum yield is either very high or very low. And in our next class we are discussing why some of the photochemical reactions are having very high quantum yield and some are having very low quantum yield. Okay, thank you for watching.